Our home planet, Earth, is a marvel of dynamic processes, many of which unfold deep beneath our feet, far from human observation. How do scientists unravel the secrets of a world we can't directly see? The answer lies in the incredible power of geodynamic modeling, a field that essentially builds digital versions of Earth to understand its past, present, and future. But this journey into Earth's hidden depths also reveals connections to other mind-bending areas of physics, including the very fabric of reality itself. Imagine trying to bake a cake without ever opening the oven. That's a bit like studying Earth's interior without models. Geodynamic modeling provides a unifying framework, allowing us to build a comprehensive story of how our planet, and others, formed and evolved. It's a grand testing ground for fundamental physics under extreme conditions so intense that even the most common planetary metal in the universe, metallic hydrogen, which makes up most of Jupiter, isn't fully understood yet, even by the smartest theoretical physicists. The beauty of geodynamic modeling is that it allows us to probe phenomena that are otherwise impossible to observe directly. Think of the churning currents in Earth's mantle, the slow dance of tectonic plates, or the fiery core. We can't drill deep enough to see them, with the deepest boreholes barely scratching the surface, a mere 12 kilometers out of Earth's 6,371 kilometer radius. That's less than 0.2%. So, we turn to numerical models. Now, a crucial truth about these models: they are, by definition, simplifications of reality. As one wise saying goes, all models are inherently wrong, but some are useful. They're not perfect replicas, but they allow us to isolate and study specific aspects of natural phenomena. It's like building a miniature car to understand aerodynamics, rather than trying to replicate every molecule of a real car. The process of creating these digital Earths is meticulous, starting with choosing the right recipes, the core equations that describe physical processes like mass, momentum, and energy conservation. These equations are typically applied to Earth's interior as if it were a highly viscous fluid, which might sound odd for something we perceive as solid rock. But on geological timescales, thousands to millions of years, rocks actually flow like very thick molasses. For brittle parts, like the crust, we use concepts like plasticity, which explains how rocks deform under immense stress, often by forming shear bands that can be interpreted as faults. Once the physical laws are chosen, scientists translate them into computer code. This involves discretization, essentially breaking down continuous equations into a finite number of points on a grid, because computers can't handle infinite complexity yet. Different numerical methods, like finite element or finite difference methods, are used, each with its own strengths and weaknesses. It's a bit like choosing between different types of hammers for a construction project. Each gets the job done, but some are better for specific tasks. A fun challenge in modeling surface features, like mountains forming or continents separating, is the concept of sticky air. Since models usually have a fixed grid, the air above the crust also needs to be modeled to allow topography to form. This sticky air isn't like the air we breathe. It's given a much higher viscosity than real air to prevent numerical difficulties, yet it's still much weaker than rock, allowing the Earth's surface to move and deform. Trying to model truly free air would be like trying to wrestle a ghost, nearly impossible with current methods. And speaking of challenges, there's the infamous drunken sailor effect in models with a free surface. This happens when the simulation's time step is too large, causing the surface to wildly overshoot its elevation in each step, leading to a kind of jiggly, unpredictable dance until the whole simulation crashes. It's a good reminder that even digital planets can get a bit tipsy if you're not careful with your settings. Before any model results are trusted, the numerical code undergoes rigorous verification to ensure it correctly solves the chosen equations. This is where analytical solutions, simple, exact mathematical answers, or community benchmarks come in. Imagine a group of bakers all trying the same complex cake recipe. A community benchmark, like everyone comparing their cakes to see if they taste similar, even if the individual baking methods differ. This helps ensure that the code itself isn't introducing errors. After verification, the model itself must be validated against observations from the real Earth. This ensures that the simplified model actually behaves like its natural counterpart. It's a constant process of refining the model, adjusting parameters, and comparing the simulated results to what we see in the geological record, seismic data, or other measurements. This step prevents models from being beautiful but probably wrong. The insights gained from these geodynamic models tie into the broader field of geophysics, which is the study of Earth's physical processes and properties using quantitative methods. Geophysics covers everything from Earth's gravity and magnetic fields to the internal structure, heat flow, and the grand phenomenon of plate tectonics. It's where the abstract world of physics meets the tangible world beneath our feet. Plate tectonics, for instance, is the scientific theory explaining that Earth's rigid outer layer, the lithosphere, is broken into large tectonic plates that have been slowly moving for billions of years. This movement is driven primarily by processes deep within the mantle, particularly by slab pull, where the denser oceanic lithosphere sinks into the deep mantle at subduction zones, dragging the rest of the plate along. It's like a cosmic conveyor belt constantly recycling Earth's surface. Early on, the idea of continental drift faced skepticism because there was no clear physical mechanism to explain how continents could plow through denser oceanic crust. It took decades of breakthroughs in seafloor mapping, paleomagnetism, studying Earth's ancient magnetic field captured in rocks, and seismic studies to validate the theory. The discovery of symmetrical magnetic stripes on the seafloor, acting like a giant tape recorder of Earth's geomagnetic reversals, was a game-changer, providing undeniable evidence of seafloor spreading and the continuous recycling of oceanic crust. The movement of these plates, from the speed of a fingernail growing at the mid-Atlantic ridge to the speed of hair growing for the Nazca Plate, is a testament to the dynamic nature of our planet. These subtle movements, over millions of years, sculpt mountain ranges, trigger earthquakes, and fuel volcanic eruptions, shaping the very landscapes we see today. But the principles of geophysics and plate tectonics aren't limited to Earth. Scientists also apply these models to understand other celestial bodies, from Venus, which lacks active plate tectonics possibly due to its scorching temperatures and lack of water, which helps lubricate fault zones on Earth, to Mars and icy moons. Imagine trying to explain why a giant ice cube might subduct into a denser fluid. It's a fascinating challenge for planetary geophysicists. And then there's string theory. This is where the universe gets really abstract. While geophysics and geodynamic modeling are firmly rooted in observable, even if indirectly, phenomena and their practical applications, string theory operates on a much smaller scale, aiming to unify all the fundamental forces of nature. It posits that everything, from the smallest subatomic particles to the vastness of spacetime, is made of tiny, vibrating strings. It's an elegant mathematical framework, but it currently lacks direct experimental evidence, making it a subject of intense debate within the physics community. The contrast is stark. One field builds digital models of planetary scale processes, while the other grapples with the fundamental nature of reality at scales we can't even dream of observing. Sometimes, in popular culture, these concepts get hilariously tangled. You might hear someone on the internet jokingly claim string theory is causing earthquakes. A prime example of confusing the theoretical vibrations of subatomic particles with the very real seismic waves that rumble through Earth's crust due to plate tectonics. Rest assured, your next tremor won't be caused by a vibrating superstring, but by the slow, inexorable march of continental plates. The journey to understand Earth as a complex system is ongoing, driven by curiosity, new data, and ever-improving computational power. From predicting natural hazards to exploring mineral resources, geophysics plays a vital role in our daily lives. And while string theory might not be causing earthquakes, the spirit of scientific inquiry that drives both geodynamic modeling and theoretical physics is the same. to uncover the fundamental rules that govern our universe, from the grandest planetary movements to the tiniest, hypothetical strings. It's a testament to how far our understanding has come, and how much more there is still to discover, both inside and outside our world. String theory is mainly concerned with fundamental physics, especially trying to unify quantum mechanics and general relativity. At present, it does not have any direct applications in geology or earth sciences. However, some of the mathematical ideas and conceptual approaches developed in string theory could, in theory, be useful in certain areas of earth science in the future. For example, the advanced mathematics from string theory might help improve computational models used in geophysics or mineralogy, especially when dealing with complex systems or very small-scale mineral interactions. The theory's way of thinking about space, time, and particles could also inspire new ways to analyze geological data or to model the Earth's interior. Additionally, if string theory leads to new tools for understanding gravity or quantum behavior, these could potentially be used to refine gravity surveys for oil exploration or to develop better sensors for detecting minerals underground. However, these possibilities remain speculative and far from practical application right now. In summary, while string theory itself is not currently used in geology or earth sciences, some of its ideas might eventually contribute to these fields, especially if they lead to new mathematical methods or technologies. But for now, there are no direct or proven applications.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.